The first page, honestly, isn't really the one that I need the most help with. I only missed one question on the first page, so
Okay.
2 questions. The second page is what I missed a huge amount of points on.
Okay. Are there
It's
any?
all limits.
Are there any? Okay. Can you read one of the limits that you missed, and we'll go through it?
Yeah, so it says the limit as x approaches 0 of 4 over 3 plus x minus 4 over 3, all over x.
Over 3. Oh, 4 over 3 plus x.
Yeah, 4 over 3 plus x. That's one fraction.
Uh-huh.
And then minus 4 over 3.
Okay. Do
And then
direct
all of that over x.
do direct substitution, and you get what? 0
0,
over
0.
0.
Mm-hmm.
Okay. So let's try subtracting those two. In other words, I don't really see anything we can factor.
Mm-hmm.
We could make this x over 1 and multiply it by both terms. I don't know, is that going to change anything? I don't think so, because we're going to have an x in the bottom over here, which is going to be infinity.
Mm-hmm.
And it doesn't matter what this is. If you got infinity that's being subtracted, you're in trouble. So let's try adding or subtracting those two terms. What's the common denominator?
Common denominator of those, that would be, like 3 times 3 plus x.
Let's leave it like that. We don't necessarily need to multiply it out.
Mm-hmm.
What goes in the upper left?
4 minus, it'll be 4 times 3, so 12.
And the upper right?
It'll be 4 times 3 plus x, so it'll be 12 times 3 plus x. Oh, no, never mind. Yeah, it's 4 times. All right.
And all over x.
Yeah.
Now, if we operate on the numerator, we end up with a minus x. That's right. Over 3 times 3 plus x.
Mm-hmm.
That's all divided by x. And now notice that if I flip the bottom and multiply, the x's go away. I'm left with a minus 1 over 3 times 3 plus x. Now substitute, you won't get 0 over 0.
Okay.
You get minus 1/9.
Minus 1/9.
Mm-hmm.
Okay.
So I guess the secret to some of these is just to do the only thing you can do. In other words, the only option I have to start this problem is to go ahead and subtract those two fractions using your rules for common denominator.
Okay.
Okay, how about, let me check my email. Still not, there it is. Finally got here.
Cool.
Yeah, it's actually a little easier to do it a different way here.
So this is the second page of the test,
Okay.
or the quiz.
You tell me where you want to start.
Probably the very, very bottom right one, number 23. That was the one that I missed 5 points on.
Okay.
I was not sure what to do.
Actually, because of all this other writing on there, is all of this purple writing yours or the teacher's?
That's the teacher's. She just handed it back to me.
Okay. Well, notice what she's doing here. I guess I don't have that much writing to do on this.
Mm-hmm.
She factored the bottom.
Mm-hmm.
So first rule of thumb is pretty much always factor if you can.
Yeah.
Okay. And now what can I do with that? It's
So with that, you.
0 over 0 after I factor,
Mm-hmm.
but I can split it into two fractions.
Yeah. So it's like sine x over x times sine x over 3x plus 2.
Well, what is it times? Remember that when I multiply these two fractions back together again, they got to equal that. So it's got to be 1 over 3x plus 2.
Oh.
See why? When you're doing math, and it doesn't really matter what level you're doing, when you do a
Mm-hmm.
process, just kind of get in the habit of doing this step. In other words, checking it. The mistake you made was actually pretty easy to make, where the second fraction I would put sine. But if I did that, multiplied it back together again, this would be sine squared. So it can't be.
Mm-hmm.
It's basically that's times 1 over that. Okay?
Okay.
Now, the reason this is helpful is you always want to try to isolate a sine x over x, because we know what the limit of that is as x goes to 0. What is it?
As x goes to 0, it's 1.
Right. So that goes to 1. This thing over here goes to 1/2. So it's 1 times 1/2, 1/2.
Okay.
Okay. Which other one would you like to do? We did 22.
Yeah, we had 22. So then let's do 20, just regular 20.
Okay. Or we can just go backwards if you want. We can do 21 and 20. You direct whichever one you have the most difficulty with. Let's do it.
We'll do 20.
Okay. Notice. Whoops. Notice. I don't know what happened. How did it switch to that mode? This is bizarre. Let me go back and pull up this file again. All right. Notice on 20, it's a very similar thing. We got to split it up into two fractions, only these are going to be, what two fractions does this split up into? Splits up into that one and this one. Now, the sine of 3x over 3x, that's the same exact problem as the sine of x over x.
Yeah.
It's still got to go to 1.
Mm-hmm.
Because as long as the argument of the sine matches the denominator, then that's the same as the sine u over u. I'm going to use a little u substitution here. I'll substitute u for 3x. But you don't really need to do that. You just have to recognize that when you see sine of anything over that same anything, that's going to go to 1. Okay, what's this one go to? 9x over 3x?
It ends up being 0 over 0.
No, not really.
If we so if you reduce it, it'd be
cancel where you can.
Yeah.
So it ends up being 3. tend to think of this as, you know how you figure out where the horizontal asymptote is on a, if I had this, 3x squared minus 1 divided by 1x squared plus 10, where's the horizontal asymptote?
Horizontal asymptote be it, I don't know, is it plus 10?
It's a 3. It's the ratio of those coefficients because the power is the same. In other words, you always look at the highest power in the numerator and the denominator, and if they're the same, then the horizontal asymptote is at their ratio, 3. Well, it's basically the same thing with 9x over 3x. The ratio of their coefficients is 3. Now, it's not, the horizontal asymptote is more as x goes to infinity, but it's the same principle. If x is going to 0, I can still cross out those and work with what's remaining. And then we know this is 1. And that's definitely not 3. Here's what 3 would be. Hold on a minute. How does this problem work? No, I won't worry about it. I'm trying to remember a problem. You got plenty of them on the page here for us to work on. So I was hoping I could be a little instructional. Okay, let's look at 21.
Sure.
Okay. Well, again, we get 0 over 0.
Mm-hmm.
Now, this is interesting. You could do it this way, the way you did it.
Mm-hmm.
That's going to get you to the right answer, I think. Did you lose points on 21? You lost 5?
I lost half a point. Half a point.
Half a point. Okay, I see. I see. I kind of like doing it this way better. Actually, that's your way also, and that's not quite right. Oh, yes, it is. Excuse me. What am I thinking? I was thinking, oh, it is difference of perfect squares.
Yeah.
That is difference of perfect squares. That's a perfect square. That's a
Mm-hmm.
perfect square. Let's separate it into x minus 5 minus 5 times x minus 5 plus 5. Now, first of all, do you see how I did that? This is not a typical difference of perfect squares problem, but it is the difference of perfect squares. In other words, this is a, this is b squared. So a has to be x minus 5, and b has to be 5. So that's where I got these two terms from.
Okay.
That's a plus b, that's a minus b.
Okay.
Okay. Now, I'm not positive this is easier, but I think it is. I think that the whole problem is going to solve itself the moment we do that, because that becomes x times x minus 10, and we have an x in the denominator, and this is where you always can cancel out things. I say cancel out, you know what I mean. I'm dividing the top by x and I'm dividing the bottom by x, which means I'm dividing the thing by 1. You can always do that. And now you have this. Now resubstitute as x goes to 0 and you get minus 10.
So I had the right answer.
You did it the correct way also. Yeah.
Oh, it looks like which.
There, exactly the same manner, factored out the x's. Why in the world should she take off a half a point?
I mean, it says like maybe I think she wants like the limits separated. So like limit as x approaches 0 times the limit limit of as x approaches 0 of x over x times the limit of x as x approaches 0 of x minus 10. I think she wanted me to split them up into two separate limits and then substitute or then solve. That's what it looks like she wrote down.
Okay, where's her right? Oh,
the little purple writing right there at the bottom.
there
I
at the
think she
bottom.
wants a second limit.
Minus the limit of x minus 10. Okay. I'm not sure why that's necessary because these x's do cancel out. So you are left with this. In other words, I don't need to separate that into two fractions any more than I needed to separate that into 9 over 3 times x over x. She didn't do that up here. Notice she could have done
Yeah.
this and didn't do it.
Yeah, who
Maybe
knows?
that was just her next step that she would have done. I don't know. But that's a little bizarre that she took off a half a point on that. Because that way
Yeah.
you did it is as perfectly acceptable as my way, and probably, in fact, it's a little easier. You don't have to worry about difference of perfect squares and things like that. Just expand it and simplify it, which is what you did. Yeah, that's disgusting. She took off a half a point for that.
Yeah. I mean, I think that's really the only thing I really messed up on this page. I mean, I messed up a plus sign on the first problem, and the third problem I missed. What did I miss in the third problem? Number 18.
Yeah, I was
I mean,
just.
I have the right answer, but
So the limit of the greatest integer function of sine x? Is that what that means?
yeah, that is.
Well,
See,
when we plug it in, it becomes the limit of the greatest integer of 0. Excuse me. We're plugging in 5, 6, or pi over 6. So if we plug it in, we get, hold on a second. Bring my writing tool up. So we get the greatest integer of sine of pi over 6. So that's 30 degrees. So she's really probably wants you to put in this step, which I see you did. What could she possibly not like about this?
I do not know.
She crossed out something here. What was underneath that?
That's that's limit as x approaches pi over 6 is what's underneath that.
So this is just a restatement of the problem, correct? In fact, that's the problem restated again. Only with pi over 6 substituted for sine x. Well, what could possibly she not like about that?
Yeah, I'm gonna have to ask her on that on Monday.
This integer of 1/2 is clearly 0. I'm trying to think as whoever takes the greatest integer function of sine x. Okay, I cannot explain why you lost points there. And you say on number 17 it was just you missed a sign? You got negative 12/17 instead of 12/17?
Oh, hold on, I was teasing. Sorry. Yeah, it's just the negative, the 25 minus 40. It should have been 25 plus 40, I guess. Near the bottom of the problem, the little purple mark right there.
This isn't even a 0 over 0 problem. No, it isn't.
No, you just substitute straight in.
Straight substitution. Okay.
Yeah, I just
5
messed
squared
up the.
minus 8 times minus 5. I like the way you do it. In other words, don't try to do that math in your head. Minus 3 times minus 5 plus 2, and then that's 25 plus 40. Okay, I see this.
Yeah, that was where I messed up. So that was just a simple mistake.
I got it. Okay, so we done with this page?
Yeah, we are.
Okay. Let's go back and see if we got any other. I do. Which one of these do you want to look at first?
The first attachment.
And which problem?
Let's start at the top, I guess.
Okay,
So
25.
I'm not sure if I lost points on 24. I don't think so, but we'll go with 25, I guess. So I guess, yeah, I'm not entirely sure.
All right, let's do 25. You lost a point for sure on that, and then I'll go back and look at 24.
Okay.
Check. Actually, let's just look at 24. Let's go. So that limit is 8.
Mm-hmm.
In other words, the limit of that minus the limit of that. So it's 8 minus a minus 3. Looks perfect to me.
So maybe I didn't lose points.
Now, the question is, what is that right there? I don't know what that means.
Maybe she started to take off point and then decided not to. I have
Perhaps,
no idea.
perhaps. Let's look at 25. So g of x, g squared of x, if we do a straight
Mm-hmm.
substitution, then it's going to be 8 squared, right?
Mm-hmm.
In other words, g squared of x means g of x times g of x. Well, as x goes to 5, that's going to be 8 times 8. So it's 8 times 8 minus 4 divided by h of x, which is minus 3. That looks like 60 over minus 3 minus 20.
So the answer is minus 20.
I think the only thing you did wrong was this part here. G squared of x, somehow you came up with 12, it looks like.
Yeah,
I know what you did. You doubled it. You did 8 plus 8 minus 4. And that's 16 minus 4, which is where you got that 12.
Okay. That makes sense.
Okay. And let's look at
26.
26.
Order of operations. Oh yeah, it's because I didn't multiply the 8 and the negative 3 first before adding the 3.
You did. Okay. PEMDAS, multiplication before addition, yes.
Yep.
Okay.
That's a silly mistake.
Let's scroll down.
So I lost.
Good with 27.
Yeah, 27's all good.
Okay, let's look at 29.
29. I lost 2 points for having an incorrect sign.
Okay, let's look at this. As we approach 6, as we approach negative 6 from the left.
Mm-hmm.
Negative 6 is the top piece of the function.
Mm-hmm.
And as we approach it from the left, definitely this function right here.
Mm-hmm.
And if we plug in negative 6, we get negative 15. And she said, then it's the absolute value of negative 15.
Yeah, so that means no negative sign.
Right. She should have said absolute value. Because just changing your sign from negative to positive doesn't always tell you why. It should have been done like that. But okay, what next? Do we want to look
34,
at
35.
Okay.
Yeah, I honestly had no idea what T would do on these.
Okay. Same principle. What that means is, where's the horizontal asymptote?
Mm-hmm.
Now, in this case, the top is larger than the bottom.
Mm-hmm.
Which means that you have an oblique asymptote.
Okay.
Okay, now that's probably not relevant here. Let's see what else we can do here. Well, what's the thing we always do if we can do it?
Substation?
Factor.
Factor.
You can't substitute when it goes to infinity.
Yeah, true.
Because you end up with a bunch of infinities cubed minus a bunch of other infinities. Those are all indeterminate. So this is not a substitution problem.
So we factor out
It is,
x on top.
well, you don't even need to do that. First of all, when you're looking for limits, the only thing that matters is the highest. All of these have no effect.
Okay.
Okay? Because as you go to infinity, the highest power dominates, totally dominates everything else. So what is this limit? X to the fourth over x to the third as x goes to infinity. Well, first of all, cancel it out, turn it into an x. So what's that go to as x goes to infinity?
In positive infinity.
And the second one, we're going to negative infinity.
Mm-hmm.
Now here, they're the same power. So I do know that this is the horizontal asymptote. And it's at 1/2, 5/10.
Mm-hmm.
Now, let's see if we can do it the limit way. Well, again, we come down to this principle that as you're going to either infinity, the only thing that matters are those two terms. Don't care about that, don't care about that.
Okay.
So, x's cancel out, goes to 1/2. And you'll notice that if I wanted to graph this, or if we looked at a graph of this, there's going to be a horizontal asymptote at 1/2. And what horizontal asymptotes mean is that's what the thing approaches as you go to the infinities, is it approaches this horizontal asymptote.
Oh,
That's
okay.
essentially what they're asking when you have the same power in top or bottom. But the only key thing you need to know with both of these problems is that the only important terms are the highest power of x. Everything else is irrelevant, shouldn't be. In other words, this becomes what's the limit of that? And what's the limit of that? It's the only thing that you look at.
Okay.
Now, I can see why you might think that if you put in negative infinity in there and cube it, you still have negative infinity, but you don't do that. You don't substitute infinities. First of all, you cross out all the x's you can of the highest
Yeah.
degree only.
Okay.
Similar to a problem such as the following. If I said, what is the limit of that as x goes to infinity.
So you would just take the x squared and the x to the fourth, or the root of x to the fourth.
Correct. In other words, you wouldn't pay any attention to that.
Mm-hmm.
And square root of x to the fourth is x squared. Now you have x squared over x squared. That's going to
So
1.
it's 1.
Mm-hmm.
So it's a horizontal asymptote of 1.
Yes.
Okay.
But it also has a limit of 1.
Okay.
And the thing that's different about that is you can't take the square root of this. I have no way of taking the square root of that. But since I'm only concerned with the highest degree polynomial, I'm only caring about that, and I cannot even consider that. Now I can take the square root of x to the fourth. Get my answer.
Okay.
All right, let's have a look at the other page. Is this the one you only...
No, I missed some of 10 points on this one. This is the last page.
Okay.
So these ones I didn't have a clue how to do.
Well,
But I think
same
that,
principle as the other two problems. Same
yep.
37 and 36.
Mm-hmm.
So notice this is not a limit problem. The other two were
Mm-hmm.
limit problems. This is strictly in behavior and asymptote problems. So in behavior means as we go to positive infinity, what does this thing go to? Now that you know what to look for.
Yeah. So for the first one, I would just take 2x squared over x squared, right?
Correct.
And then I'd cancel out x squared, so I'm left with just 2.
Correct.
So
And
that means,
that's the end behavior because it's going to go to 2 whether it's going to negative infinity or positive infinity.
okay.
Okay, so
Now
that
how do I find the vertical asymptote?
vertical asymptotes always come when the denominator is 0. So factor this into x plus, oops. Hold on. X minus 3 times x minus 2. And now tell me where the denominator is 0.
Where the denominator is 0?
Huh?
It's 0 at when x equals 3 and x equals 2.
So you have two vertical asymptotes at x equal 2 and x equal 3.
Okay.
Okay? And horizontal asymptotes. Where's the you also have a horizontal asymptote on 38.
So it would just be the same as the end behavior model, which would be 2.
Correct.
Okay.
And then the function is going to be hyperbolic in nature, and it might look something like this. And then it'll do something in the middle, probably go up like that, and then it'll come down like that. In other words, once you have all your asymptotes, then drawing the graph is just drawing on your new asymptote grid.
Yeah.
Drawing
Okay.
a hyperbolic function. They don't ask you to graph it here, but once you have the vertical and the horizontal asymptotes, graphing it becomes a piece of cake. Okay, so 39, what's the end behavior?
So it'd be 6x cubed over 8x.
Correct?
Over 8x, and then you cancel out x's first.
Correct?
So that'd be 6x squared over 8, and that would be 3x squared over 4.
The numbers aren't going to matter.
So just x squared?
Correct.
Okay. So you always cancel out coefficients on that, no matter what?
Only when you're talking, no, not always. If
Okay.
these were the same power,
Mm-hmm.
then it's going to go to 6/8. But the fact that the numerator dominates the denominator, in other words, this thing's equal basically to x squared. Well, what happens to x squared as we go to positive infinity?
It goes to positive infinity.
What happens as we go to negative infinity?
Positive infinity.
They set each of these up a little strange because usually in behavior you need a as x goes to positive infinity and another one as x goes to negative infinity. But they made all of these the same, so it doesn't matter. And number 40, the bottom has a higher power than the top. What does that mean? Your vertical or your horizontal asymptote? Let's look at end behavior first.
So would that be 4x over x squared for 40 to start out with?
Actually, 4x over minus x squared.
Minus x squared. That's right. Okay.
Okay.
So
And
again,
it will matter here. Because as we go to, no, it doesn't matter. As we go to positive infinity, what's this thing go to?
Oh geez, just set positive infinity as well.
You have infinity in the denominator and you have a number in the numerator. What's it going to?
I don't know.
0. In other
0.
words, yeah, as x gets bigger and bigger and bigger and bigger, this whole thing gets closer and closer to 0. Notice that if x is 1,000,000, we have 4 millions. If x is 1,000,000,000, we have 4 billions. Well, if x approaches infinity in the denominator only, then you can know that that goes to 0. And it doesn't matter whether it's going to negative infinity or positive infinity. It's still going to 0. So again, we only need one answer for end behavior. Now, vertical asymptotes, that's correct. Whenever x is 1, that denominator is 0, and whenever x is minus 1, that denominator is 0. It's disappointing that she wrote -2 on the only part that you got right.
No, I think it was the -2 was just for the overall problem.
Okay.
The slashes are through the other ones.
Horizontal asymptote is where, when the denominator is bigger, actually you only need to look there to figure out what the horizontal asymptote's got to be.
So what is the horizontal asymptote? Just 0?
Y equals 0.
Y equals 0.
If you put just 0, she'd take a point off, definitely. Having seen what she took a half a point off on the previous problem. She's not going to give you any leeway at all. But it's, first of all, the horizontal asymptote is an equation of a line. It is not a point. Just like a vertical asymptote is an equation of a line. And in fact, I'm surprised she didn't get upset with you not saying this. Instead of, this, the way you wrote that, x equal 1 comma minus 1. Not sure that the reader knows that that's two different equations of lines. I guess they do. It's awful easy to misinterpret that, as there's 2 points on the x-axis that we care about. One of them is 1, the other one is -1. But that's not what it is. What it is there are 2 vertical asymptotes. There's not 2 points on the x-axis that we care about. We care about those 2 dotted lines. And only this expresses them. And maybe what that came from right there. I don't know. Maybe not. Because like I said, I have no idea whether she'd take off for that or not. I'm not even sure if it's incorrect, to be honest. All I know is that it could be confusing a little bit.
Okay.
This kind of indicates, not really. That should work, actually.
Okay.
Right, let's go on.
This is the one that I actually did not know how to do, so I left blank. Lost 10 point. No, I lost.
The bonus question?
Yeah.
Okay. You've arrived at the bonus, not the store. So, what are we looking at down there? F of 1? It looks like a 1 next to the F.
Yeah, it's like F1 because the calculator, the way it graphs it, it just said like
Okay.
the first graph.
Okay. So the first graph, determine and verify algebraically the right-hand end behavior. Okay, well, right-hand end behavior comes from as x goes to positive infinity.
Mm-hmm.
Left-hand end behavior is as it goes to negative infinity. So let's just do this the way I like to do it. Positive infinity cubed minus 1 over e to the positive infinity, correct?
For the whole thing?
No, in other words, all I'm doing is trying to figure out the right-hand end behavior algebraically, starting with that function. So the right-hand end behavior means as x goes to infinity. So I'm going to find the limit of that function as x goes to infinity. That's the same question. That's what right-hand end behavior means. It means the limit of x cubed minus e to the minus x as x goes to infinity, positive infinity. That's what right-hand end behavior means.
Okay.
Well, here I can substitute it because when I substitute it in this part, that part goes to 0, does it not?
1 over e to the infinity?
And whenever you have infinity in your denominator and you got a number in your numerator, it goes to 0. It doesn't matter if it's negative infinity or positive infinity. It's going to 0.
Mm-hmm.
Okay?
Okay.
So what's positive infinity cubed?
Positive infinity?
Minus 0, positive infinity. So the right-hand end behavior is that. Now, if I look at that graph, it's not that obvious. It's hard to make your eyes look left and right. But that's what you have to do. It's really easy. I notice this is one of the more difficult things for students to do, which is to make sure your eyes are looking the right way. It's very difficult to look at this graph on the left here and not look up and down. In other words, I can tell that y is going to positive infinity as I go in this direction. So yes, the graph confirms that we're going to positive infinity.
So how would you verify algebraically?
This way right here.
So that's the okay.
This is the verification algebraic.
So would I have to like write limit as x approaches infinity of positive infinity?
I do it exactly the way I do it here. They don't like substituting infinity like I do, but I've never seen a problem with it. As long as you're aware of indeterminants. In other words, if you get infinity over infinity, that's not determinable. But if you get positive infinity cubed, that is. Now let's substitute negative infinity. since I'm substituting negative infinity, I can write that like that. Now I got a problem. I got
The e to the infinity.
infinity minus infinity. Oh, that's not a problem. That's negative infinity. It's negative 2 infinities. Same thing as negative infinity.
Wait, so how do you know that the e to the infinity is negative infinity?
It's not negative infinity. It's positive infinity.
Oh, okay. Yeah.
Any number raised to the infinite power, if that number is greater than 1, is going to infinity. If that number is between 0 and 1, it's going to 0. But we know e to be 2.7. So if you take 2.7 and raise it to the infinite power, it's going to infinity. So,
Okay.
and negative infinity cubed is indeed negative infinity, because it's a negative times a negative times a negative. So sometimes that sign does matter if you have odd exponents. And if we look at this graph over there, we can see that the graph confirms our algebra. It shows it going to negative infinity as x goes in that direction. Okay, so we've done this one. What's this at a different scale?
Which one?
What's the middle graph? Ah, it's a different function.
No, the way she has us the way she had us verified algebraically in class is a little different. They always make us take so if you have like x squared minus e to the negative x, then you would take, if you want to verify the left end behavior, then you use the use the most powerful part of the function going to the left over on the bottom, and then you essentially substitute verify that way. And then if you want to verify to the right, then you use the strongest function going to the right, put that in the denominator, and verify that way.
Okay.
And
not sure that's any different.
Yeah, I'm just not sure if she'd be okay with this method or not.
Okay, I see what you're saying. In other words, to see what this limit is as x goes to infinity, that's the strongest term. That's the only one we care about. That goes to infinity, correct? That's what she's saying? And
I guess so.
And then as we go the other way, the only problem I see with her method is that how do I know which is the stronger as I'm going to negative infinity? How do I know that this isn't stronger than this?
I think that's why she gave us the graphs, I think.
Ah. Well, so if I'm doing this one here algebraically, you're saying that as x goes to positive infinity, I'm going to use that. But how do I know if that's the x cubed or the minus e to the minus x?
Yeah, I'm just as confused.
That's why I like my way better. My way leaves no confusion at all.
Yeah.
However, since I'm the only one that knows my way, I don't really know your teacher's way. Let's continue here with this second one. So all I'm going to do, I'm going to do two steps. I'm going to plug in infinity in that equation. Is that supposed to be a minus x exponent?
It looks like it, yeah.
Okay.
Yeah, it is.
If I'm plugging in infinity over infinity cubed. Now, do I have a problem? Not really. What's the numerator go to?
Negative infinity.
No. always rewrite these. This is the same as minus 1 over e to the positive infinity.
Oh,
That's what
so
that
it goes
that's
to
what
zero.
that is. Yes,
So it
exactly.
goes to zero.
Goes to
Zero over infinity.
infinity, that definitely goes to 0. You got 0 in the numerator, infinity in the denominator. In fact, whenever you have infinity in the denominator and any number at all in the numerator, it's 0. The only time it
Yeah.
isn't is if you have infinity over infinity. And calculus has a way of handling those. You just haven't learned it yet. It's called L'Hopital's rule. Whenever you have 0 over 0 or infinity over infinity, there's actually a real easy method. It's just that you don't get to that method until after you complete differential calculus. So there's a catch-22 in them teaching it. All right. So we figured out that this goes to 0, and we can tell by looking at it graphically that it goes to 0. So if we do it the other way, now I've got minus e. I'm substituting negative infinity, which gives that. And I got negative infinity there cubed, which becomes negative infinity. Now that's a problem. That's infinity over infinity. Or it's actually negative infinity over negative infinity. However, exponential growth is greater than polynomial growth. In other words, if I have this, 2 to the x over x, what's the limit of that as x goes to infinity?
So 2 to the infinity, so infinity over infinity.
It's going to go to infinity because the numerator is going to outperform the denominator. If you start putting in numbers, put in 10 for x, and then put in 100 for x, and then put in 1,000 for x, your numerator blows up. Your denominator does not. Another place where I'm not sure they've taught you this, but it goes to infinity. And in fact, it appears to go to infinity in 2 different places, right there and right there. Which is saying what? It's saying that the left-hand end behavior is definitely infinity, as we've just shown algebraically. And there's also a place as we approach 0 where it goes to positive infinity. In other words, there's a vertical asymptote right there. And as we approach 0 from the right, we go to negative infinity. But since the only thing they asked about was right-hand and left-handed end behavior, we don't care about this point right here. Now, again, how you're going to prove that to her, I don't know. That's tough because they haven't taught you what you need to know to prove it to her.
Yeah, the way that I can't remember exactly how her method works, but there's a different way that involves some sort of weird.
She's claiming that's the more powerful function as opposed to this. And so you use this only, that goes to infinity. Or excuse me, that's the one I made up. Over here, same difference. First of all, the negative signs do cancel. And we've got basically e to the infinity over infinity. And e to the infinity, being an exponential function, is far more powerful her words, I believe, right? You did
Mm-hmm.
say that whichever is the more powerful function. There's some interesting stuff that it's worth talking about. Just got a few more minutes rather than tackling this thing over here.
Ooh, I found the way that she wants us to do it. It's so for one of our review packets. So if you're given y equals e to the x minus 3x, to verify the right end, it says ex is the strongest one, and left end is negative 3x is the stronger one. So you put e to the x minus 3x over e to the x, and then you solve algebraically until you end up getting like 1 minus, essentially until the whole thing solves out to 1.
Okay.
So you split e to the x over e to the x minus 3x over e to the x, and then you get 1 minus 3x over e to the x, and then I guess somehow you simplify that to 1, or to 0, then you get 1 minus 0 is 1.
All right.
And that's how she wants you to algebraically verify these.
The best thing you can do is look at her example there. Let's see, it's 10 o'clock. If you want to do the third one, I'm happy to stay longer.
Oh no, it's okay.
You're good to go?
I think I'm good. I just need to figure out her method better, because I'm sure, I don't know if she'd like yours because it's easy.
Yeah, you'll have to figure out hers. I'm not sure I understood all that, but I kind of get what she's doing. But just before I go, there is something interesting. Exponentials are always more powerful than polynomials. And believe it or not, factorials always outperform exponentials. In other words, if I said, what's the limit of this? I know the numerator is going to blow up. Even though I've got an exponential in my denominator, those blow. You see what exponentials graph like. They go up fast.
Mm-hmm.
They don't go up as fast as factorials. You know what 50 factorial is?
No.
More molecules than exist in the entire universe.
10 to the 64th?
Actually, 3 times 10 to the 64th, yeah.
Wow.
That's pretty amazing. Factorial growth is impressive. You'll get to this eventually, but just to show it to you. So you have algebraic growth or power growth, which is what that's called. You have exponential growth, which is what that's called, and you have factorial growth. And if one is in the denominator and the other is in the numerator, you can always figure out the end behavior by which is the more powerful function.
So which one of those is the most powerful? So factorial is the most powerful?
By a lot.
And then exponential.
This was e to the x over x factorial. Then that's going to go to 0 because the denominator blows up faster than the numerator.
Okay. And then exponential is the second most powerful.
This is slightly different. This is not a number to an exponent, a variable exponent. This is the x to the x. Well, that actually does better than that. Because notice, if you had 10 factorial, that would be 10 times 9 times 8, whereas 10 to the 10th is 10 times 10 times 10 times 10 times 10. So if you have x to the x in the denominator, that's the fastest of all, the most powerful of all. But that's a rare one. Usually you're looking at this situation over here, where you have some number to a variable exponent, and then you have that variable exponent factorial. The factorial is always going to grow faster.
Okay.
Okay? Greg, I will let you go, and hope this online worked out for you.
Yeah. So how do I go about paying you?
Well, do you have a PayPal account?
Yeah, my mom does, yeah.
Here, let me show you exactly how to do it. If you go to my the easiest website to use is my digital math tutor. That's the one that you probably want to use from now on, especially since you're doing online. It's real easy to pay. Go to my front page, scroll down to where it says buy now, hit it, pops open another page where you can enter the amount. And then it'll pop open, for your mom, it'll pop open just the PayPal. Okay. So
Okay.
price per item, I can see why people are having problems with it. It's 36 for an
Okay.
hour online. But after I hit 36, let's see what happens if I try to do it. I'm going to do this, and then I hit continue, and now it should pop open my PayPal screen and let me put in my password. Then you're done. That's it.
Okay.
2 steps.
All right. Cool.
Okay. So digital math tutor. Yeah, that's what's on the business card that I gave you. That's
Yeah.
probably the one you've been using.
Yeah.
Although I know that Nick Darrow originally started with my Algebra to Calculus tutor, which is another website that I use more for in-person.
Okay.
But there you go.
All right. Cool. Thank you very much.
And if you like, I can send you an on-voice, although you really don't need it.
Yeah.
If you just follow that procedure I just showed you there,
Yeah.
that'll take care of
Should
it.
be good.
Okay?
All right.
All right, Greg.
Sounds good.
Good luck. Talk to you later.
All right. Thank you very much.